Shaders have a very specific functionality in the OpenGL pipeline. Hence, they have inbuilt variables and functions to help you out. One such built-in variable is the GL position. Its value must be defined in the vertex shader. Here is an example of vertex shader program. While we have defined an in variable vector4 which has the vertex positions, we assign these vertex positions to GL position, which is a built-in variable in the shaders. The input vertices location is given by the four-dimensional vector v position, whose specification includes the keyword in to signify that its value is input to the shader when the shader is initiated. There is one special state variable in our shader, GL position, which is the position that will be passed to the rasterizer and must be output by every vertex shader. Because GL position is known to OpenGL, we need not declare it in the shader. Notice here that there is no definition of GL position. It's a predefined built-in variable. There is also a predefined variable in the fragment shader, but this is on max only. This variable is GL underscore frag color. Its value must be defined in the fragment shader if you're using max. Each invocation of the vertex shader outputs a vertex. Each fragment invokes an execution of the fragment shader, and each execution of the fragment shader must output a color for the fragment. Here is a small fragment shader program for max where we have assigned a color, RGBA color, to GL frag color without defining the variable GL frag color because it is a built-in variable. GLSL also provides inbuilt operators and functions, including standard C functions such as trigonometric, arithmetic functions like normalize, reflect, length. Overloading of vector and matrix types is also present. For example, if we define A as mat4 and B, C, and D as vector4, we can multiply vector B with matrix A and assign it to another variable which is defined as vector4. We can multiply matrix A with vector B. We can also use swizzling and selection in GLSL. That is, we can refer to array elements by their indices using square brackets or by using the selection operator, which is dot. For example, in an array we may have XYZW values or RGBA values or STPQ values. And that vector is basically a four-dimensional vector, vec4. So m square bracket 2 means we are referring to the third element because the indexing starts from 0. So m2 is basically the same as m dot b if it is a RGBA vector, or m dot z if it is XYZW vector, or m dot p if it is STPQ vector. The swizzling operator lets us manipulate components easily. For example, if we have A as a vector 4, we can assign values to YZ like this, skipping the X and W values. And we can also alter the values of a vector and make them like BGRA instead of RGBA by just using v dot BGRA. So using the dot operator, we can not only refer to one element, but we can refer to multiple elements at the same time and in any order. So we could have had A dot YX and assigned the value of Y first and then the value of X. We could have had Z, X, Y and then assign those values in that order. And similarly, we can refer to A dot Z, X, Y, and hence we are referring to the values in a different order and store them in another variable. So swizzling allows us to manipulate the components of a vector easily. Swizzling does not work with matrices. You can instead access a matrices fields with array syntax. For example, the square bracket 1 will access the second column because indices starts from 0. The matrix 2, 0 sets the first entry of the third column. On the other hand, the result of the first array accessor is a vector, so you can swizzle that. For example, mat3 the matrix, and the matrix 1 is basically the second column, and you can swizzle that and arrange or assign its elements y, z, x in a different order, the values of 3, 1 and 2.